Continuing on with lecture notes 3, we're going to talk about hypothesis testing. First, what's a hypothesis? A hypothesis is a question that can be answered with a yes or no, or a statement that is either true or false. For example, do hourly earnings for econ graduates equal $20 per hour on average? Does adding fertilizer to crops improve crop yields? There are more green than red M&Ms in a bag of M&Ms on average. These are all questions we can test. We can run some experiments and then get some answers. Are they true or false? They're not subjective. Are these hypotheses? 30 minutes of daily exercise improves health. Sort of. This one's a little confusing because it's vague. In theory, you could say this is a hypothesis, but what you really need to do is define what health means. Whoops. Let me get my writing device going here. Define what health means, and then what is exercise. We need to put some parameters on this. Chocolate is better than vanilla. Not a hypothesis, because this is subjective. Driving faster is more dangerous. Driving faster than what? And more dangerous than what? Driving slower or jumping out of an airplane? It's not really a hypothesis. A null versus an alternative hypothesis. So a null hypothesis in the context of the mean, or the population mean, takes on a specified value denoted h0 or h0. And we'll write it as the expected value of y is equal to mu y sub 0, this bit here. An example, I hypothesize that the average student height at CSU is 5 foot 8 inches. So I would write my null hypothesis like that. The expected value of height is equal to 5 foot 8. This is compared to an alternative hypothesis, which specifies that what is true if h0 is false. So a two-sided alternative hypothesis is just we'll put, instead of h0, we'll put h1. Expected value of y is not equal to mu y naught. So it's anything else. So we could say a one-sided hypothesis. We'll be dealing with two-sided hypotheses in this class. A one-sided would just be expected value of y is greater than mu y 0. The not equal means it could be less or more than the null hypothesis. An important note: we never fully accept the null. We never say that our null is true. We can only say that we've failed to reject the null with a certain degree of confidence defined by the probability distributions that we're working with. This means there's always some chance, based on sampling error, that our estimate is incorrect. For example, there's always a chance the sun won't come up tomorrow. If we have a random variable that is the sun coming up every morning, so far, as far as history goes, as far as we know, the sun has come up every single day. And we've taken draws every single day of this random variable. But there's always the chance that it doesn't come up tomorrow. So scientists are taught to never say they have discovered something with certainty. There's always some probability, albeit often very small, that the findings are incorrect. All right, the sample variance. So far we've talked about the sample average. Now we need to talk about the sample variance, which is an estimator of the population variance. S squared y is an estimator of sigma squared y. So this is the population variance. This is the sample variance. And it's defined by this equation here. S squared y is equal to 1 over n minus 1 times the sum of yi minus y bar. Remember, this thing is sample average squared. Right, so this looks a lot like the population variance, where the population variance is expected value of y minus its mean squared. Looks a lot like the population variance, but we're replacing mu y with y bar. We could put yi in there. and then we're dividing by 1 over n minus 1. The sample divides by n minus 1, and it's a correction for a small downward bias that comes from estimating y bar. This is a degree of freedom correction. What it really amounts to is we have used up 1 degree of freedom in estimating y bar. In the notes, I show that this is an unbiased estimator of the population variance. So I show this in the notes if you're curious. So remember, in the previous set of slides, we looked at what does unbiased mean. Unbiased for y bar meant that it was equal to the population mean. Here we have the sample variance is equal to the population variance, and the expected value of the sample variance is equal to the population variance. The sample standard deviation, well, just like the standard population standard deviation, so our population variance is this. The population standard deviation is just, whoops, I should not do that. Take that guy out. Population standard deviation is just the square root of that. So the sample standard deviation is the square root of the sample variance. And then the standard error of the sample average y bar is an estimator of the standard deviation of the sampling distribution of y bar. So the standard error is 1 over root n times the standard deviation of the sample standard deviation. So a recap of the sample variances. We've defined 3 of them. We have the sample variance, this thing here, which is an estimator of the population variance for y. The sample standard deviation, which is an estimator of the population standard deviation of y. So here, for these two, we're talking about the random variable, the random variable y, the underlying random variable. The sample standard error is the standard error of y bar, which is an estimate of the standard deviation of the sampling distribution of y bar. So the third one, we're talking about the distribution of y bar, the sampling distribution.